Hello everyone, I'm Dr. Mehraei, and today we are going to talk about the statistical inference. Let me remind you about this slide that we had before. So we usually have a population which contains some parameters. Some of them or all of them are unknown to us. That's why we take a sample or several samples from this population in order to come up with these statistics and use them in order to predict or estimate the parameters of our population. These procedures that we should take for estimations and even the tests that we will run in order to compare maybe two populations together or estimate just one parameter inside the population, we call it a statistical inference. There are several methods for estimations, and we already know about point estimation, but let me introduce you with two famous ones, and after that we will talk about the confidence interval. Okay, so two of them which I wanted to tell you about are method of moments and method of maximum likelihood. So for the method of moments, we have such scenarios like we have population moment as our new notation. We can show it by mu, one index that we have here, and this index shows the power of our variable inside the expectation. So if I have mu1, moment 1, it is expectation of x power 1. If I have population moment 2, I have expectation of x power 2. And these population moments, we want to make them equal to the sample moments in order to find the estimations for our parameters that we are interested in our population. So at the end, we should make mu k's equal to m k's, which are population parameters and our statistics. And we have another term named central moments, and these are the corresponding formula to that. For the previous one, if you look at the sample moment, you can see this one. If I consider m1, this is exactly to x bar, right? So sample moment 1 is equal to x bar. In case of central moments, we have the case we showed them by prime, and in case of m2, we will have the definition of variance. But as you know, for the sample, we prefer that we have n minus 1, not 1 over n. So we should have n minus 1 in that scenario. So what's the goal here? At the end, we should have such equations. We make the population parameters as population moments equal to the sample ones. And we will have set of equations. So let's see in that example that how we can estimate them. Assume that we have such a distribution. This is the CDF of that distribution. And we want to estimate theta and sigma, and also find first and second population moments. In order to do that, first thing first, we should get the derivative of CDF in order to have our PDF. So we get the derivative of that one, and this is the final answer. So you see, you should go through the things that you learned from calculus in order to calculate derivatives and integrals, which we use a lot in this course. And then in order to find the first population moment, we need to get EX. Why the power is 1? Because this is the first population moment. Second one, we should have power 2. So integral is starting from sigma. Why not minus infinity? Because here this is the condition inside this distribution. Okay. So we calculate this one, and since we want it to be positive under the curve, and that's why we consider theta to be more than 1 in this case, and theta more than 2 in this scenario. So as soon as you find the answers for mu1 and mu2, you should make them equal to the sample ones, m1 and m2, and estimate theta and sigma in terms of m1 and m2, which we wrote here for you. Okay, so it was an example regarding the methods of moments. For method of maximum likelihood, this is what we are doing here. And we should be careful whether we are dealing with a discrete distribution or continuous one. In case of discrete one, we have such a formula. First of all, we should have multiplication of the point probabilities. Since if we are taking the simple random sampling, since we are taking such a sampling, then in that case, since they are independent, then you can write them point-wise like this. So the multiplication would be multiplication of all of the points together. Otherwise, if they were not independent, we were not allowed to multiply them point-wise like this. But this is very hard to calculate it, especially when we have lots of variables and parameters inside. So because of that, we get logarithm from that formula, from that equation, in order to simplify it. So when I have such a notation, it means that multiplication. This is not summation. This is multiplication of my terms. In this case, when I get ln, this is the property of ln or logarithm that when we have multiplication, we can change the format into summation, and we should write the ln separately in that scenario. So please go through the properties of logarithm in order to understand this part perfectly. For example, Poisson distribution, we know that this is a probability mass function. This is a discrete distribution. So we can apply that. This is the formula regarding that distribution. We calculate the multiplication and apply ln to it. N is logarithm with base e, right? You remember that. Okay, so when you apply to it, it means that for each one of these terms, I can convert them into summations instead of multiplication. So ln of e power minus lambda, this is minus lambda. Ln of e, we know that this is equal to 1. You can bring back the power inside the argument of the ln into the backside of the ln like this, and you can write this one. So this part plus multiplication will change to plus, and when we have division, it will turn to subtraction. So ln of lambda power x, the power of x can be bring back to the outside of the ln to multiply by ln, and we keep lambda like the way it is, and so on. So when we are reaching the final answer for this PMF, then we should get the derivative of that one and make it equal to 0. This is the theorem inside calculus that when we want to find maximum or minimum of a function, then we should get the derivative of that one, first derivative, and make it equal to 0 in order to estimate that. So now let's see. For our maximum likelihood estimator for lambda hat, whenever we use hat, it means that this is the estimation for lambda, right? So this one is equal to, when after we calculate this one, it shows that this is equal to x bar. So we bring lambda to the other side of the equation, and we understand this is 1 over n and summation of xi, which is x bar. So this is the proof to show you that mean of Poisson for case of population as a parameter, this is equal to lambda. If you want to estimate that, that's the reason we make lambda equal to x bar for finding the parameter for our Poisson distribution. And we can apply the same thing for sigma power 2 as well in order to prove that this is equal to lambda as well. Okay, in case of continuous distribution, like PDF, in that case, we should define everything in terms of intervals. And we can apply the same method in order to find and estimate our parameters. Okay, good news for you guys is that I'm not going to ask you for either of those methods, for methods of moments and methods of maximum likelihood. It's not because I'm kind, it's because I believe that you won't need to prove that y, for example, the mean of the population for Poisson distribution is equal to lambda. As engineers, you need to apply them to solve problems regarding your own fields. That's why as much as you know about it, I don't need you to be evaluated about proving these things. proving such parameters by using these methods is rare for students who are studying statistics or mathematics. There are pure statisticians who are dealing with such problems. That's why I'm not going to evaluate you for those methods, but it's nice to know. That's why I talked about it. It's inside the scope of this book to talk about it, but I'm not going to evaluate you guys for those methods. But the thing you should know for sure is confidence interval, because we should use these intervals in solving lots of engineering problems, and especially for hypothesis testing, we need them very much. Okay, so let's learn about confidence interval. Let's look at these terms. An interval A to B is a 1 minus alpha 100% confidence interval for the parameter theta if it contains the parameter with probability 1 minus alpha. What is this alpha? Alpha is our type 1 error. We will talk about later. So in an example, I will show you better what we mean by that. But look at this one, which is important. The probability of theta, the parameter, which is between A to B, is equal to 1 minus our error. So this is the way that you can find the confidence level of your confidence interval. So this is called confidence level, 1 minus alpha. Now, in this example, it will be more obvious. Like before, if you remember, I was interested to estimate the mean of the population, which was the height of all students in method. In order to do that, I took a sample from our class, for example, and I understood that the mean of our sample is 165 centimeter, and we call it the point estimator of my population, X bar. Now, I understood that the population parameter was 167 in reality, and I had error for 2 centimeters. In order to compensate such problems, we can define confidence interval. And even I can say, for example, for 95%, I'm sure that the parameter of my population will fall inside this interval. What I'm doing, for example, 165 minus plus 5. So 160 centimeters and to 170 centimeters maximum. So this is an interval that I constructed, and I can say in which confidence level I'm sure that I predicted correctly that the mean of my population will fall inside this interval. But the thing is that how did I understood I should add or subtract 5 from this one? How did I understand this is 95%? These are the things that we should talk about in details in the next slide. So what it means here, it means that if I construct such intervals, because I can take different samples from the university, maybe if I take it from another class, I will construct another interval. So for 95% of cases, the population parameter, which is 167, if I know about that information, falls inside my interval. Okay, so as you can see, I can construct different intervals for the same parameter. And in one case, maybe you see it gets out of the range. So theta is outside the interval that I predicted, even for 95% confidence level. So it means that 5% I may make a mistake. So from one population, when you want to predict or estimate the population parameter, maybe you need to take several samples from the same population in order to estimate it. For example, for the height of students, as our example that we mentioned, if I take the samples from different classes, not just your class. If for your class, I found X bar 1 is equal to 165 centimeter. Maybe in another class, I find out that the mean of the sample X bar 2 is equal to 166 centimeters. In another class, a different sample mean. So not only X can have a distribution, X bars, the sample mean, can also have a distribution as well. And that's what we call sampling distribution. So to make a z-score out of x, we know that we subtract from mu and divide it by a standard deviation. In case of x bar, if I am interested in order to make a z-score, so I will have x bar minus mu x bar, which is mu itself, they are equal to one another, we proved that before, divided by sigma of x bar. What is sigma of x bar? This is sigma over square root of n, which is the sample size. So this part is different from the time that we wanted to make this score out of x. This is x bar, not x. So x bar minus mu over sigma over the square root of your sample size. This is the way that you make this score out of x bar. Now, time to time in our confidence interval, you will face such a case that inside the parentheses, we write, for example, z parentheses 0.95. What it means? This is different from the one that we asked you, like, what's the probability of x less than, for example, something, then we convert it into probability of z less than something, and we read it from the table. This is the vice versa case. Let me show you inside the table. Like, for example, I want to find about what's the z-score corresponding to 95%. So the probabilities are inside the table, not on the marginal parts. So if I want to find that, I should look for 95%. When I look it up, I will find it like somewhere here, right? Between these two, 1.64, 1.65. So what to do? Which one of them I can choose? There are several methods in order to approximate it. One way is to find the closest one. Both of these two are the closest one. One way is to find the average between them, which is a good idea. You can also use it in the exam. So we can find the average of these two, which is 1.645. So 645, 645 would be, 1.645 would be the answer for the z-score. So between 1.64 and 1.65, you can see, you can say 1.645. Another way is to approximate it accurately using the similar method as we use for the box plot. You remember the extra part of the decimal point, then I multiplied with the difference of these two. This is also the best way. This is actually the best way that we can use, but in the exam, you can simply just get the average of these two, and that's good enough. So 1.645 would be the answer of that one. All right, so let's see how we can construct confidence intervals for population mean, mu. Case 1, so there are different scenarios. We should check the conditions very carefully. If the population is normally distributed and the variance of population is none, this is case 1. If this is the case, first of all, I know about my how to calculate standard error and my mean. And by the way, this part we call a standard error. I will show you in the interval. Okay, so let's see how we construct. First of all, I should consider my point estimator, x bar, minus plus. So whenever I want to construct the confidence interval, I can write minus or plus here in order to calculate both of the scores. Minimum is here, maximum is here. So the negative one, x bar minus this part of the number, I call it precision. The part related to z is called reliability factor, and the part regarding this part, standard error. So point estimator, this part reliability factor, this part is standard error. The whole thing that you subtracted and plus to your point estimator is called precision. Okay, what does it mean, z alpha over 2? First of all, it should be inside parentheses. It would be better. So it is exactly this one. So when I say alpha over 2, if for example alpha is 5%, it means that this one, because alpha over 2, if alpha is 5%, 1 minus alpha will make this one. And it doesn't matter if you calculate it for alpha or 1 minus alpha over 2. I mean, if it is alpha over 2 or 1 minus alpha over 2, because this is a symmetric distribution, you will subtract or add to it, so it doesn't matter if inside the formula you write 1 minus alpha over 2 or alpha over 2. It will give you the same answer at the end. Okay, so we should find this z-score from this probability, which is named alpha, and multiply this by a standard error, sigma over square root of n. In the examples that I will solve for you in the tutorial, you will learn it much better. At the moment, I understand this is vague, but see example 9.13 inside your book, so that they already solved one question regarding it, which is useful for you guys. So what we should notice here is that we have information about our variance of population sigma. This is actually a standard deviation because we got the square root of that, and we put it here. All right, so this alpha that we use inside this formula, this one helps to say how much is your confidence level. So 1 minus alpha percent is your confidence level. Okay, case 2 scenario. The population is normally distributed, or maybe not, we don't care. So it doesn't matter what's your distribution of your population. The variance of population is unknown. Okay, this is problematic. And the sample size is big enough. This is good news, because we can use central limit theorem in order to approximate it with normal distribution. So you see, the formula is almost same, but instead of sigma, which is the standard deviation of the population, I should approximate it with the standard deviation of the sample. But we can read it again from the standard normal distribution table. So read these intervals very carefully to see what are the differences between these intervals that we define. Okay, case 3. If the population is normally distributed, the variance of population is unknown. Okay, this is a problem, as we said, but we have more problems here. The sample size is not big enough. By the way, when I say big enough, usually we consider it more than 30, and this is based on our taste. Usually in most of the books they consider more than 30, sometimes 25. In some examples, it depends on the case that you are studying. Maybe even 100 number of data, we think that is not big enough. It depends on the study that you are doing. But generally speaking, we could say after about 30 or equal 30, we say this is good enough as the sample size. Okay, so if this is not big enough, in that case, because I don't also know about my variance of population, but luckily the population is normally distributed. In that case, they introduce a distribution named T-student distribution or T-distribution. So I should find the T-score instead of Z-score. There are some differences between T-student distribution and normal distribution. They look very similar. They are good. The T-distribution is very good for approximation for a standard normal distribution, but there are some differences I will show you later. And one of them I can even say now is that we should know about degree of freedom. There's a term named degree of freedom, and you can easily calculate it by using your sample size. So for case of one population, it's always n minus 1. And for case of two populations, I will show you later. So for making a T-score, what's the difference? This is very similar to Z-score. And instead of sigma, I have S. For even the case that I use central limit theorem, exactly we use the same formula here, even with S. So it's important at the end that we should read it from the T-student table, not a standard normal distribution table, in order to calculate this reliability factor here. The standard error is the same, the point estimation is the same, but this one is different whenever you construct your confidence interval. So we should know how to calculate these actually T-scores as well. In case of Z, 95%, we could just read it from the normal standard distribution. For T-student distribution, we should know about degree of freedom as well. For example, if the sample size was 21, so n minus 1 is 20. So how to read it from the t-distribution? This one is very different from what we knew for standard normal distribution. On the left side, we have degree of freedoms, sample size -1, and above it, forget about two tails. But we will talk about it in hypothesis testing, but read it from the one tail for the time being. So for this one, you can find out about the probabilities. Yeah. For standard normal distribution, the probabilities were inside it. The z-score were on the left side and above. For t-distribution, the probabilities are written above, degree of freedom on the left side. These are the t-scores. So for example, for case of 95%, we should get the complement of that one. For case of 5%, for example, we have degree of freedom 10. You can read it from here easily. So you see, these are the things that we can do for t-distribution and insert it inside the confidence interval. We will talk about them in details and how exactly we find these values in the tutorial. Okay, so the case number 4 for estimating population mean of the population, and we by constructing the confidence interval. Okay, in case of 4, if the population is not normal distributed, okay, this is a big problem. Variance of population is unknown, okay, and sample size is not big enough. Too many problems. If, for example, the population was normal distributed, it was the t-distribution case, right? But this is not normal distributed. If, for example, the sample size was big enough, I didn't even care that this one is not normal distributed. I could use central limit theorem, but so many problems here. None of them are helpful. So I should use non-parametric method, which is outside the scope of the book. We won't talk about it. Okay, so the thing that we mentioned was just about one population. Sometimes we have two populations and we are interested to compare them to one another. The best way to do that is to compare the difference of their means. To see, for example, if there is a significant difference between these two populations or not. So that's why we have such a thing, like parameters for population 1, mu x. Sometimes they show mu1, mu2 for different population, mu x or mu y, doesn't matter. And sigma power 2x, sigma power 2y. This one belongs to population 1, this one belongs to population 2. And we get samples separately from them, and we get the statistics out of this population by taking the sample. And for the second population, we do the same. Then we want to estimate the difference between population means. This is important. So this is what we are looking for. We are looking for the estimation of the difference between population means, not the population sample. These are the ones that we took from the population. We can calculate them easily. The difference between two means of the population is our problem. Okay, so there are different scenarios again. We should check the cases, the condition of the cases to understand which confidence interval we should construct. Okay, case 1. Both populations are normally distributed. Very good. The variances of population are known. This is very good. We have all the information to construct this confidence interval and read it easily from normal standard distribution. Take a look at this one. We find the sample mean of the first population. So we take a sample, we find the mean of that sample, subtract it. Then we have the sample mean of the second population. So this is the mean of the sample related to the second population. Then you can use minus in this side of the interval to get the minimum value, your lower bound. And here you will add it to this precision. So this one you can calculate it by finding the z-score from your z table. The same situation here. So you see these two are exactly the same number. You just here subtract it, here you add to it. Inside this part of standard error, here the way you can calculate them. The variance of the populations, you have the information about them. Divide them by the sample size of your first sample for the first population, and this is the second sample from the second population. So this sample size is related to first sample, first population. This is your sample from the second population. This is the size of it. Okay. The second case, both populations are normally distributed or not, so we don't care about the distribution for our population. Why is that? Usually this is the case when the sample sizes are big enough and I can use central limit theorem. So in the previous formula, instead of sigmas, I can use s power 2 for first sample. So variance of the first sample, variance of the second sample from the second population. So easily I can estimate them by that. So I don't care if the variances of the populations are unknown in that scenario. Case 3. Both populations are normally distributed. The variances of populations are unknown. This is bad. Sample sizes are not big enough. Okay, this is bad news too. If either one of them, n for the first population or second population, these are the sample sizes. If each one of them is less than 30 or both of them, this is a problem. And it means that the sizes are not big enough. If your first sample is 50, the other one is 10. So again, it's considered that this is not big enough as sample size. And another condition, variances of two populations are equal. I don't know about their value, they are unknown, but they are equal. This information I know. How it happens? Sometimes I divide my population into different segments, and I know the variances are equal, but I don't know exactly what is the value of that. Such cases happen. So in that scenario, first of all, I should use t-distribution, not like case 1 and case 2. I should use t-distribution, and I should use a standard deviation, pool the standard deviation, which we show by SP. So pool the standard deviation. And in order to calculate it, I provided you the formula here. You should know about the variance of your first sample, variance of your second sample, which is from your second population. So when I say first sample, it means that just the only sample you took from your first population. And when I say second sample, I mean the only sample you take from your second population. And degree of freedom here, look at this one. Sample size 1 plus sample size 2 minus 2. See? The summation of sample sizes subtracted by 2. Case 4. Both populations are normally distributed. The variances of populations are unknown. This is bad. Sample sizes are not big enough. This is very bad. Variances of two populations are not equal. Lots of problems. But the good news is that these populations are normal distributed. That's why I can use a distribution which is the approximation of t-distribution. This is out of the scope of the book. I won't ask you about this scenario. Just for you guys to know, we can still calculate. Case 5, populations are not normally distributed, not like the case number 4, and it has its other problems in case 4 as well. The variances of populations are unknown. I don't even care if they are equal or not. The populations distributions are not even normal. Sample sizes are not big enough either. So in that case, again, I should use non-parametric methods, which we don't cover in this course. Okay, guys, I know I covered several topics intensively. It was actually in the syllabus of your course. That's why we had to cover many things in one session. You should go through lots of things in 1 week, and you have lots of studying to do. I know it looks scary at the beginning, but after you practice them, especially after the tutorial, you will see confidence intervals are one of the easiest topics in the statistics. After that, we will have hypothesis testing. So it's very important for you guys to start studying about these topics from now, because all of them are related to each other. If we don't understand about confidence interval, there is no way we understand about hypothesis testing. So hopefully after tutorial, as I say, everything will be smooth for us. and hope to see you guys in the next lecture.